Time series analysis is a fundamental concept in econometrics, and understanding it is crucial for analyzing and forecasting economic phenomena. Concept of time series analysis in econometrics. Time series data consists of observations on a variable collected sequentially over time at regular intervals, e.g., daily, monthly, quarterly, annually. Examples in economics include GDP, inflation rates, stock prices, unemployment rates, interest rates, and exchange rates. The core idea behind time series analysis in econometrics is to 1. Understand the underlying structure and patterns in the data. This involves identifying components such as trend, the long-term upward or downward movement in the series, seasonality, regular and predictable fluctuations that occur within a fixed period, e.g., higher retail sales during holidays, cycles, irregular fluctuations around the trend, often associated with business cycles, expansions and contractions, irregular or residual variations, unpredictable, random fluctuations not explained by the other components. 2. Model the temporal dependencies. Unlike cross-sectional data where observations are independent, time series data exhibits autocorrelation or serial correlation, meaning that observations at one point in time are correlated with observations at previous points in time. Econometric models for time series data specifically account for these dependencies. 3. Forecast future values. A primary objective of time series analysis is to predict future values of the economic variable based on its past behavior and the identified patterns. 4. Test economic theories. Time series models can be used to test hypotheses about the relationships between economic variables over time. For example, investigating how changes in interest rates affect inflation over subsequent periods. Key challenges and considerations in time series econometrics. Stationarity, a crucial concept. A time series is stationary if its statistical properties, mean, variance, and autocorrelation, do not change over time. Many econometric models require stationarity for valid inference. Non-stationary series often need to be differenced, transformed, to achieve stationarity. Spurious regression. Regressing a non-stationary series on another independent non-stationary series can lead to a seemingly strong relationship that is purely coincidental and has no economic meaning. Model selection. Choosing the appropriate model, e.g., ARMA, ARMA, VAR, based on the characteristics of the data and the research question. Diagnostic checking. After estimating a model, it's essential to check its adequacy by examining the residuals for any remaining patterns, especially autocorrelation. What is AR1 process? AR1 stands for Autoregressive Process of Order 1. It is one of the simplest and most fundamental models in time series analysis. In an AR1 process, the current value of a variable is linearly dependent on its immediately preceding value, plus a random error term. Mathematically, an AR1 process for a time series y_t is defined as y_t equals phi_0 plus phi_1, y_t minus 1 plus epsilon_t, where y_t is the value of the time series at time t, y_t minus 1 is the value of the time series at time t minus 1, the previous period. Phi_0, phi naught is a constant term, intercept. Phi_1, phi 1 is the autoregressive coefficient, representing the impact of the previous period's value on the current value. Epsilon_t, epsilon t is a white noise error term which satisfies the following conditions. E_t equals 0. 0 mean y_t equals sigma squared. Constant variance. CoV epsilon_t epsilon_s equals 0. For t in EQS, no autocorrelation. Epsilon_t is typically assumed to be independently and identically distributed. IID. Derivation and interpretation of the AR1 process. Derivation. The AR1 process itself is not derived in the sense of being a consequence of more fundamental principles. Rather, it is a specification of a stochastic process. Its form is chosen because it captures a common type of temporal dependency where the past directly influences the present. However, we can derive its key properties such as its mean, variance, and autocorrelation function under the assumption of stationarity. 1. Mean of a stationary AR1 process, E of y underscore t. If the AR1 process is stationary, its mean, E of y underscore t equals mu, is constant over time. Taking the expected value of the AR1 equation, E of y underscore t equals E of phi underscore 0 plus phi underscore 1 y underscore t minus 1 plus epsilon underscore t. Mu equals phi underscore 0 plus phi underscore 1 E of y underscore t minus 1 plus E of epsilon underscore t. Since the process is stationary, E of y underscore t equals E of y underscore t minus 1 equals mu, and we know E of epsilon underscore t equals 0. Mu equals phi underscore 0 plus phi underscore 1, mu plus 0 mu. 1 minus phi underscore 1 equals phi underscore 0, mu equals frac phi underscore o, 1 minus phi underscore 1. This mean exists and is constant only if phi underscore 1 less than 1. If phi underscore 1, GE1 the series is non-stationary and its mean would not be constant or finite. 2. Variance of a stationary AR1 process, var y underscore t. If the AR1 process is stationary, its variance, var y underscore t, equals gamma underscore 0, is constant over time. We can also assume, without loss of generality for variance calculations, that phi underscore 0 equals 0, i.e., we analyze the process in terms of deviations from its mean. Let's consider the equation y underscore t equals phi underscore 1, y underscore t minus 1 plus epsilon underscore t, assuming phi underscore 0 equals 0 and y underscore t is in deviation form. Taking the variance of both sides, y underscore t equals var phi underscore 1, y underscore t minus 1 plus epsilon underscore t. Since epsilon underscore t is independent of y underscore t minus 1, y underscore t equals var phi underscore 1 y underscore t minus 1 plus var epsilon underscore t, y underscore t equals phi underscore 1 to the power of 2 var y underscore t minus 1 plus sigma squared. Since the process is stationary, y underscore t equals y underscore t minus 1 equals gamma underscore 0. Gamma underscore 0 equals phi underscore 1 to the power of 2, gamma underscore 0 plus sigma squared, gamma underscore 0, 1 minus phi underscore 1 to the power of 2 equals sigma squared, gamma underscore 0 equals frac sigma squared, 1 minus phi underscore 1 squared. This variance exists and is finite only if phi underscore 1 less than 1. This condition, often called the stationarity condition, is crucial for an AR1 process to be weakly stationary. 3. Autocorrelation function, ACF, of a stationary AR1 process. The autocorrelation function measures the correlation between y underscore t and its lagged values y underscore t minusc. The autocorrelation at lag is denoted by rho underscore k equals frac of y underscore t minusc, var y underscore t. Let's derive rho underscore 1, autocorrelation at lag 1, v underscore t, y underscore t minus 1, equals e, y underscore t minus mu, y underscore t minus 1 minus mu. Substitute y underscore t minus mu equals phi underscore 1, y underscore t minus 1 minus mu, plus epsilon underscore t, v underscore t, y underscore t minus 1, equals e, y underscore 1, y underscore t minus 1 minus 1, equals e, y underscore t minus 1 minus mu. Since epsilon underscore t is independent of y underscore t minus 1, and thus of y underscore t minus 1 minus mu, e epsilon underscore t or y underscore t minus 1 minus 1 e, y underscore t minus 1 minus mu, to the power of 2, equals phi underscore 1 var, y underscore t minus 1, equals phi underscore 1 gamma underscore 0. Now for rho underscore 1 equals frac covey of y underscore t minus 1, var y underscore t equals frac phi underscore 1, gamma underscore 0 equals phi underscore 1. For rho underscore k, autocorrelation at lag k, covey of y underscore t terminus equals e y underscore t minus mu, y underscore terminus minus mu. We can recursively substitute the AR of 1 equation y underscore t minus mu equals phi underscore 1 y underscore t minus 1 minus mu plus epsilon underscore t y underscore t minus mu equals phi underscore 1 y underscore t minus 2 minus mu plus epsilon underscore t minus 1 plus epsilon underscore t equals phi underscore 1 to the power of 2y underscore t minus 2 minus mu plus phi underscore 1 epsilon underscore t minus 1 plus epsilon underscore t. Continuing this Fock steps, y underscore t minus mu equals phi underscore 1 to the power of k of y underscore t minus mu plus phi underscore 1 to the power of k minus 1 epsilon underscore t minus k minus 1 plus dots plus phi underscore 1 epsilon underscore t minus 1 plus epsilon underscore t minus 1 plus epsilon underscore t. Now taking the covariance with y underscore t minus mu, covey of y underscore t minus equals e phi underscore 1 to the power of k of y underscore t minus mu plus text terms involving epsilon underscore t dots epsilon underscore t minus k minus 1 y underscore t minus mu. Since the error terms epsilon underscore s are independent of y underscore r for r less than s, covey of y underscore t minus equals phi underscore 1 to the power of ke y underscore t minus mu to the power of 2 plus e text terms involving epsilon underscore s text and is y underscore t minus mu text where sget minus plus 1. All terms involving epsilon underscore s where sget minus plus 1 will have zero covariance with y underscore t minus mu because epsilon underscore s is white noise and independent of past values of y. So covey of y underscore t minus equals phi underscore 1 to the power of k var y underscore t minus equals phi underscore 1 to the power of k gamma underscore 0. Finally, for rho underscore k equals frac covey of y underscore t terminus var y underscore t equals frac phi underscore 1 to the power of k gamma underscore 0 equals phi underscore 1 to the power of k. This shows that the autocorrelation function of an AR1 process decays exponentially with the lag k. Interpretation 1. Persistence/memory. The AR1 process implies that the current value of y underscore t is directly influenced by its immediate past value y underscore t minus 1. The coefficient phi underscore 1 quantifies this persistence. If phi underscore 1 is positive, a higher than average value in the previous period, y underscore t minus 1, tends to lead to a higher than average value in the current period, y underscore t. This signifies positive autocorrelation or momentum. If phi underscore 1 is negative, a higher than average value in the previous period tends to lead to a lower than average value in the current period. This signifies negative autocorrelation or reversion. 2. Stationarity condition phi underscore 1 less than 1. If phi underscore 1 less than 1, the effect of past shocks epsilon underscore t diminishes over time. The series tends to revert to its mean, mu equals frac phi underscore o 1 minus phi underscore 1. This is a stationary process, meaning its statistical properties are stable over time, making it predictable and amenable to standard statistical inference. If phi underscore 1 equals 1, the process is a random walk, or unit root process. Y underscore t equals phi underscore 0 plus y underscore t minus 1 plus epsilon underscore t. In this case, the effect of shocks persists indefinitely, and the series does not revert to a mean. It is non-stationary, and its variance grows over time. Many economic series, like stock prices or exchange rates, are often modeled as random walks. If phi underscore 1 greater than 1, the process is explosive. The effect of past shocks grows over time, leading to an unstable and unrealistic series for most economic contexts. 3. Role of phi underscore 0 intercept. The constant term phi underscore 0 determines the mean of the stationary process. If phi underscore 0 equals 0, the mean of the stationary process is 0. Otherwise, the series fluctuates around a non-zero mean. 4. Role of epsilon underscore t, error term. The white noise error term, epsilon underscore t, represents unpredictable shocks or innovations to the series. It captures all the factors influencing y underscore t that are not explained by its own past values. These shocks are assumed to be random and independent over time. In summary, the AR1 process provides a simple yet powerful framework for modeling time series data, particularly when there's a strong direct link between current and immediate past observations. Its properties, especially stationarity, are crucial for proper econometric analysis and forecasting.